Welcome everyone to the 9th ESSI-BJ online seminar of the webinar series on things to come that is dedicated to space missions, ongoing space missions and future space missions from international space agencies. We have today Professor Giovanna Tinetti from UCL. Thank you, Professor Tinetti, for accepting our invitation. And you can see in the webcam also the ISSI-BJ Executive Director, Professor Ip. As I said, this is the 9th webinar of the series, and before we start with the lecture, I would like to briefly introduce ISSI-BJ and also the streaming platform so that things work smoothly for everyone. So ISSI-BJ, the International Space Science Institute, Beijing, was established in 2013 thanks to the collaboration between the National Space Science Center of the Chinese Academy of Sciences and the International Space Science Institute in Switzerland, Bern. Since then, we have organized every year a wide array of events, including workshops, international teams, forums, and unfortunately, last year we could not organize any because of the current pandemic, but we hope it's gonna get better very soon, that we will able to have more in-person meetings this year. In the meanwhile, we have started this webinar series with outstanding scientists from all over the world, and also we've started another webinar series in Chinese with outstanding female Chinese scientists. So I would like to say a couple of words about this platform, and then I will give the floor to Professor Ip. If the streaming is not smooth, you can use the link that I have shared in the chat box, which is Bilibili, a Chinese streaming platform. It should work very smoothly, and ideally you should use Chrome or Firefox and shut down the antivirus. So without further ado, Professor Ip, and thank you very much once again.
Yeah, thank you, Lola. So thank you very much. We are very happy today we have able to invite Professor Giovanna Tinetti to give us a talk on this very exciting mission called Ariel. And later, I'm sure she will tell you what Ariel is. But first, I will say a few words about Professor Tinetti herself. But I just learned that she grew up in Torino, Italy. And she went to University of Torino for her graduate study. And she is now in the University College London. But before then, she after getting her PhD, she went to NASA JPL as a postdoc. And then she worked at ESA. And then she got a very highly prestigious research fellowship from the Royal Society before joining UCL. She's now in the head of this astrophysics department, right, of the astrophysics group of UCL. But most importantly is that she's the principal investigator of this very important mission to study the atmosphere of exoplanets. And then so if you want to know everything about exoplanet, the atmosphere, here is Professor Giovanna Tinetti, please.
Thank you so much, Professor Ip, for this very kind introduction. And thank you in particular for the invitation today. I'm really honored to give this talk this morning or afternoon, depending where you are on Earth. So in the past, more or less 25 plus years, we have learned that planets are ubiquitous in our galaxy. And today we're counting more than 4,000 exosolar planets around our stars. And it's not just that the number of exoplanets being discovered that is quite impressive, and this exponential growth in terms of numbers is in particular the fact that if we're looking at the parameter space of these planets and also their orbital configuration, they all seem to be quite different from the planets in our own solar system. So we're seeing a much greater diversity in terms of planet and star and orbital parameters compared to our own solar system. And these two graphs I'm showing here are trying to convey this message, just looking at some of the parameter, like the planetary radii, semi-major axis, or the distance planet star, or the planetary mass. Now, in the next decade, if 4,000 is not enough for you, then in the next decades, we should really prepare to go for really tens of thousands of new exoplanets being discovered, because we have a suite of space missions that are already operating or about to be launched to discover new planets. So in particular, at the moment, we have TESS, the NASA TESS, and also ESA-CHEOPS that are operating, both discovering planets, but also refining some of their planetary parameter. And very soon, we are waiting for the James Webb Space Telescope to be launched that will deliver exquisite spectroscopy for some of the very best exoplanet discovered so far. And later on, the Payload mission will deliver even more planets, in particular, more Earth-like, which are the Graal, if you're interested in habitability. But today we will talk about another mission, as Professor Heap has mentioned before, and the mission is Ariel. And Ariel will be launched in 2029, and you see Ariel in this time graph here. So the science objective of Ariel haven't really changed since the original proposal when we submitted it to ESA in 2015. And the reason for that is, despite the fact that we have so many planets being discovered so far, unfortunately, we still know very little about most of them. And so these questions that we put in the original proposal, because we believe are really a key question to be addressed by astrophysics in the next decade, are still unanswered. And so what Ariel will try to answer is, what are exoplanets made of? And what are the physical processes that are shaping the planetary atmospheres? But also, we want to take a statistical view and use this information to answer a broader and more general question, which is, how do planet and planetary system form and evolve in our galaxy? Because we believe that all this diversity that we're seeing must be somehow connecting to the formation evolution processes. So Ariel will focus on measurement of atmospheric chemistry for really a large sample of exoplanets, about 1,000 at least during the lifetime of the mission. And the idea is really to use the atmospheric chemistry, but also atmospheric structure, as a tracer of the nature and history of the planets in our galaxy. For many of the planets discovered so far, in particular, what we called in jargon sometimes the super-Earths or sub-Neptunes, which are objects in between the size of the Earth and the size of Neptune, we still don't know what is the nature of those planets. Are there big terrestrial planets? Are there small Neptune? Somewhere in between? And clearly knowing their atmospheric chemistry will help us to understand really the bulk composition and the nature of the planet. But also, I mentioned our interest to put some constraints on the formation evolution processes of planets in the galaxy. And again, the atmospheric chemistry, there is can be really used as a pointer to address those questions. There is an entire literature at the moment. It's a very hot topic, because there is a suggestion that if we can measure the elemental composition, in particular the giant planets, and we compare this elemental composition to the one of the star, then we might be able to work out the provenance of these planets, where in the disk they form in the first place, because we believe that the chemistry is a fossil sort of information of what happened during the history of the planet. And of course, this diagram here is very complex, because it's trying to convey the kind of complexity that we believe being behind the formation evolution processes of all these planets. And we still don't know exactly, in particular, the super-Earths and sub-Neptune, how they're formed. And by understanding their atmospheric composition, we'll have some important insight into these extremely important questions. Okay, a few words about Ariel. Ariel, we proposed it in 2015. It was selected to be the ESA M4 mission in 2018, but it was adopted formally by ESA in November 2020, so very, very recently. Ariel will be launched in 2029. It will be launched in L2. And Ariel is a 1 meter class telescope. We're talking about an elliptic telescope made a cast grain of axis made of aluminium. And the key selling point of Ariel is the ability to do a simultaneous coverage, spectroscopic coverage between 0.5 micron in the visible down to 7.8 micron in the infrared, and really use the simultaneous coverage to understand the composition, the atmospheric composition, the atmospheric structure of thousands of exosolar planets being observed. And among these thousands of exoplanets that we want to observe, we want to make sure that both rocky and gaseous planets are being included in our sample, planets that are as cold as 300 Kelvin up to 3000. So clearly we want to make sure that we are probing different regime for the chemistry, and so different temperature, but also different type of stars from A to M. And so making sure, again, that we have a statistic view of the planet and star in our galaxy. The Payload Consortium that will build the payload of Ariel is composed of 17, will be built by 17 ESA countries, and we have an ESA contribution from the KST. A few words on why we selected the spectral range and also the resolution for the spectrograph that we have designed for Ariel. There has been a lot of studies when we proposed Ariel, and then after the first selection, to optimize the spectral coverage, but also the resolution and what kind of signal we want to be able to extract out of this atmosphere. And in this graph, I tried to put together some indication of why we're selecting 0.5 to 7.8. In the visible wavelengths and near infrared, we are very sensitive to the presence of clouds. And so if clouds are there or hazes, we want to be able to detect them and also characterize them. In the visible wavelengths in particular, we can have also the information about the star. And if the star is active, we know that unfortunately sometimes the activity of the star can cause some issues on the spectra for the planet. But we can correct for the activity if we have simultaneously also the information in the optical wavelengths. And of course, in the near infrared and in the infrared more specifically, there are really, there is a long list of molecules that are absorbing, and in particular, all the molecules that we're interested in, carbon-bearing molecule, oxygen-bearing molecule, nitrogen, sulfur-bearing molecule, they're all absorbing on these wavelengths. And so clearly have this broad wavelength coverage is extremely important to have a good picture of this atmosphere. But we also want to make sure that we are probing different temperature regime, and the ability to go to the infrared also give us the chance really to probe the thermal structure of these atmospheres. So in the lifetime of the mission is 4 years, but it could be extended to 6. But our strategy has been optimized for the moment for the 4 years. And we want to take a 4-tier approach because we want to make sure that during the lifetime of the mission, we have a good statistical view of a large population of objects, but also in-depth information about a smaller sample of these objects to understand a little bit better some of the mechanism behind formation and evolution. And so we want to start with a survey, what we call Tier 1, where we want to look at roughly 1,000 planets, as I said, selected with different parameters, stellar and planetary and orbital parameters. And we will initially start with low resolution because we want to have an overview, first of all, of what fraction of planets have clouds or not. Also to answer questions like, is hydrogen still present or not in this atmosphere? You don't need to have a very high resolution. And this is actually a very important question, in particular for small planets, to understand whether hydrogen and helium have been retained from the protoplanetary nebula originally, or on the contrary, hydrogen was lost in time and there is a secondary atmosphere. But we also want to do more classical color diagrams and see whether they have been very successful to classify stars. So we want to see whether they could be of any help also to provide a very zero-order classification of planets. Now, out of the survey, we want to select half of the targets, roughly 500, and at that point to go into the deep survey, and so observing them at much higher resolution. And with this information at this point, with this spectroscopic information, we can work out what are the main atmospheric components, but also the trace gases of these atmospheres. We want to be able to probe the thermostructure, the cloud characterization, and for the giant planets, we'll be able to look at the elemental composition. But as I mentioned before, we believe could be an important insight into the formation and evolution processes of the giant planets in particular. And then we want to select between 50 and 100 targets, in particular the gaseous planet for which in one transit or in one eclipse you can get exquisite signal to noise. Then the idea is to monitor this subset through time to get some information about the atmospheric circulation and spatial and temporal variability. So clearly repeating observation through time will give us a chance to see how variable are these atmospheres. And finally, for a subset, we want to monitor the planet while it's orbiting around the stars. So basically recording some phase curves, spectroscopic phase curves. And clearly for these planets, we'll be able to have a pretty in-depth understanding of the circulation and the dynamics of these atmospheres as a function of orbital phases. And so, again, for a subset of objects, we want to be able not just to do transit and eclipses, but also phase curves. So I have just some example to show you the aerial performances, but if you're interested in that, we have published plenty of paper, in particular, what is called in jargon the Red Book that was submitted in November as part of the adoption process. And it's an interesting document that one can read because it's a summary for the science and also design of the instrumentation of all the work that the consortium has done so far. But just to give you some idea about the aerial performance, if we're looking at individual planets, the one that will be observed through tier 2, 3, or 4, so basically in-depth spectroscopic characterization. Then we did a lot of papers, and also we had some data challenge for the retrieval to make sure that our science objectives, when we declare that we want to be able to extract the thermal structure of this atmosphere, but also how some of the chemical abundances are changing as a function of pressure. Indeed, this is the case. And all the simulations that were presented in the Red Book and in many other papers that have been published really show that the design of the mission is able to deliver what we wish in terms of science. These are some other examples for some planets observed in this case through phase curves. Again, for phase curves, we will be able not only to have a very good understanding of the chemical composition and thermal structure of the atmosphere at one point in time, but also to monitor how this thermal structure and the chemistry in particular are changing as a function of the orbital phases. We did also many simulations with the tier 1, which are low resolution measurement. But even at low resolution, color diagram or other more AI-oriented techniques seems to suggest that you can use very well the tier 1 results as a discriminator of some classes of objects in terms of which objects are cloudy or, on the contrary, seems to be more transparent, and for which the atmosphere is more transparent, or also have a very preliminary classification in terms of chemical composition. We also did quite a lot of simulations to make sure that when we look at a population of objects, a population of spectra, then we can extract some characteristics out of the population and not just out of individual objects. And so in particular, in the simulation that I'm showing you here, that were led by Quentin Changea, what was done was to run simulation for hundreds of gaseous planets with a different chemistry, and then we injected some chemical trends in the population. So for instance, in this particular case, we have imposed in the simulation that there was a linear trend between the temperature and the abundance of water vapor. So that there was the abundance of water vapor was proportional to the temperature. And we'll be able to recover this trend and other similar trends that we inject in the data. So it really shows that in principle, if there are these trends in the many hundreds of planets that we will observe, we will be able really to extract this information, which is one of the key selling points of the mission, the ability not just of observing individual planets without precision and accuracy, but also to have a statistical view of population of objects. And this slide is just to show that in particular for tier 2 and tier 3, we are quite confident that the molecular abundances that we are able to detect with Ariel, it's really extremely precise, and so it's good enough really to put some good constraints on all the chemical models that many teams around the world are now working on to predict the characteristic of these exosolar atmospheres. I mentioned that we're very interested to understand the link between the atmospheric chemistry and formation processes. And again, we did many simulations to see whether there is such a link and whether Ariel will be able to detect that. And so whether the precision with which we can extract the elemental abundances will be enough really to put some constraints. And again, in particular for the gaseous planet, this is possible. And we looked not just at the CO ratio, which at the moment has been very well studied quite a lot in the literature, but we looked also at other elemental ratio like C over N or S over N, and so on and so forth. Clearly, I mentioned already at the beginning of the seminar, small planets, so in particular planets in between terrestrial planets and Neptunes, so the one that we're calling in jargon super-Earths, sub-Neptune, in part to hide our ignorance, are still a big mystery. We have so many questions about those planets. We don't know whether hydrogen is still there in many of these objects, and this is very important to know because it can clearly make a distinction between more Neptune type or sub-Neptune type and on the contrary, more rocky or oceanwards. And so clearly being able to probe the atmospheric composition is extremely important on top of knowing the density of these objects. And so clearly we are looking forward looking at all this information for a large number of small planets. BNL2 is very valuable for the thermal stability, but also because of the sky visibility. And from L2, you have a great view of the sky. We can cover the entire sky throughout the year, and the instantaneous field of view is 100% towards the galactic pole and drops to 40% towards the ecliptic. But we are confident that in particular, all the objects that we already have and will be there as a net effect of the result of tests and Cheops and Plato will be well distributed, and so we'll really have the chance of monitoring all these objects very efficiently. And in fact, talking about aerial targets, so these are the prediction of type of targets in 2029. So we are expecting to have, these are conservative extrapolation. We expect to have at least more than 2,000 targets to select from for T1 planets. And again, I'm sure you hear just the planetary parameter, but also we looked at stellar parameters and the parameter space of stellar, planetary, and orbital parameters will be really quite complete. Already today, we have more than 600 planets that Ariel will be able to observe very efficiently. So clearly, going to 1,000 in a decade will be relatively easy. We are already planning some mission reference sample, which is basically our strategy of observation, and we are already simulating what we should prioritize in terms of either diversity and completeness in the star-planet parameter space, or on the contrary, a mission that is a bit more focused on certain questions. And the reason why we're already doing this quite in advance is because we don't want to be caught unprepared. We want to have in our hands many possibilities, depending also how the field will evolve. And so we are now confident that if we want to prioritize diversity and completeness in our sample, then this will be possible through the 4T strategy. But also if we want, on the contrary, to put higher priority in the study of smaller planets, that also will be possible. It means that perhaps the overall number of planets being looked at in the lifetime of the mission will be less. But again, this is a discussion that will continue inside the consortium with ESA, but also with the entire international community interested in exoplanets. Of course, we are also very interested in synergies between Ariel and many of the facilities that in the next decade will provide new information about exoplanets. And obviously, an obvious example is JWST, but also the Hubble Space Telescope. And I think there will be a lot of synergies and complementarities with these two facilities. Well, Hubble hopefully will still last, and clearly Hubble can provide UV spectra, and this is a regime that Ariel cannot do. So clearly, if we have Hubble still operating for a bit of time, will be absolutely fantastic. In terms of James Webb, if we are comparing performances of Ariel and James Webb for warm and hot planets around bright stars, then they are pretty much similar. Where James Webb is clearly much more optimal is in the study of Harwell planets in the habitable zone, so small planets and cold one. That's really where having a big dish is really helpful. But Ariel will concentrate more on warm and hot planets, and in particular bright stars. So I think there is an obvious complementarity between these two facilities. We also want to make sure we will use all the information coming from ground-based facilities, in particular the ELT or TMT, that are expected to see first light in the next few years or so. From the ground, you can extract spectra at extremely high resolution, possibly even getting some isotopical abundances. But you do that typically in a very narrow wavelength range. On the contrary, from space, you typically, and certainly Ariel will be able to do that, Ariel will be able to deliver a broad wavelength range in one shot. which is great for the continuum. But then if you put them together, then you can use them in synergy and really have the big picture, but also the high level of detail that from the ground facilities will be able to deliver. We have many simulators to be able to simulate the performance of Ariel and making sure that well, the design now is pretty stable, but we'll keep monitor throughout all the rest of the construction phases and until launch to make sure that the performance, the scientific performance that Ariel will deliver are indeed what we're expecting. And also we want to deliver to the community, to the open community, a web interface simulator. So the entire community very soon will be able also to simulate the performance of Ariel. And so if they want to check whether they have a scientific question and they have some simulated data that they want to see, whether they could be observed with Ariel or not, that will be possible very soon, not just for people in the consortium. And this brings me to this slide where we want to make sure that the interaction between the Ariel Consortium and the ESA science team and the international community is very strong between now and launch and post-launch. And in particular, we want to make sure that also Ariel data will be delivered to the open community very soon. And in fact, we'll have all the data that will be recorded during the science demonstration phase will be released immediately after quality control. So no proprietary period for the consortium. And the same will happen for Tier 1 data. They will become public immediately after quality control is completed. And we're talking about basically data for roughly 1,000 planets for the entire sample. Tier 2, Tier 3, and Tier 4 data will be, we expect them to be slightly more difficult to process. And so because of that, we have a 6-month proprietary period after quality control. And then the data, of course, will be released also to the public. Between 5 and 10% of the Ariel time will be available for our science. And this time will be allocated by ESA through some open calls. In these calls, the consortium has no say. And there will be a proprietary period for the proposal of 6 months. But again, the consortium will absolutely not involve in this call. It seems like science fiction that in January 2020, we were able to host an open conference in ESTEC, where we had more than 200 participants from 19 countries. And it was absolutely marvelous. So we're really looking forward to do another Ariel open conference. Clearly now it's not possible because of COVID restriction, but hopefully 2022 or whenever it will be possible is certainly something that is very high up in the priority of the Ariel Consortium to have another open conference and get the feedback and the input from the open community. In terms of targets, since the list of targets that Ariel will be able to observe is changing very rapidly because of the results from tests and from KEOPS and our service from the ground. So again, very soon we will have the Ariel Catalogue being publicly available through an interactive website. So again, later this year, this will be available together with the Ariel exposure time calculator that will be again available to the open community. In 2018, we launched the Ariel Data Challenges. And in particular, the Machine Learning Data Challenge was extremely successful. We had more than 100 international teams of professional amateur machine learning experts. And the 3 winners were awarded at the European Conference of Machine Learning in September 2018 and also at the Exoplanet conference. We plan to have another data challenge in 2021. The challenge will be out in April. So if you're interested in machine learning AI, make sure that you pay attention to April. Of course, we will inform the entire community of both as astronomers, but also planetary scientists and machine learning experts through all the mailing list, because we want to repeat this exercise because it was extremely successful, very useful also for the mission. We also have a number of citizen science programs, and in particular, the Exoclock one has been very, very successful. This is a program that we have initiated in collaboration with the public and amateur astronomers, because we are aware that for many targets that Ariel will observe, the ephemerides are not very precise, because some of these planets were discovered with a specific survey, but then they weren't monitored again through time. And if you don't do that, very rapidly you lose the precision of the transit time. And so potentially, if this is left by itself and is not corrected, you might end up missing the transit in the right place when you're trying to do the observation. And so you're clearly decreasing the efficiency of the program. And we clearly don't want to do that. And most of the time, you don't need to have big platforms in order to follow up this transiting planets and measure the ephemerides precisely. And Exoclock is exactly doing that. At the moment, we have really hundreds of participants that are very interested from all the world. And through the website, you have the complete list of planets for which we really would love to have more measurements and what are the priorities, how to observe them, depending on the facility you have access to and where you are in the world. So if, again, you're interested, this is certainly a very useful and also a fun exercise. Okay, I believe my time, it's over, so let me start to wrap up to conclusion. Exoplanet appears to be ubiquitous in our galaxy. This is something that we learned in the past 25 years or so, and I think it's a very strong message. It means that we really have a lot of work to do if we are interested in exosolar planets. The number of discovered exoplanets is really increasing exponentially, but unfortunately, we still know very little about them. And because of that, really going for the atmospheric composition, the atmospheric chemistry is really the next obvious step that we need to take in order to understand the nature, the history, the formation, and evolution of these planets. And Ariel has really been conceived to deliver this very first chemical survey of about 1,000 exoplanets, so really going for the large statistics. And really we want to be able to probe a sample that is quite diverse in terms of planetary, stellar, and orbital parameter. Before the launch of Ariel, as I mentioned, the Ariel Consortium and the ESA team, we are all very interested in getting the input and the feedback from the international community. So this is most welcome. We want to make sure that the science goal, the science objectives, but also the strategy for observation of the mission really stays fresh until the launch. And so we are really planning to have regular open workshops, data challenges. We want to get information from the community about selection of best targets. And we'll make sure that all the tools that we have been generating in the consortium will be available to the community, including exposure time calculator, interactive website, and so on and so forth. And after launch, I think Ariel really offer a very open data policy, and certainly want to make sure that a great fraction of the data will be available immediately after quality control, so without proprietary period, and at least 5–10% of the time will also be available for other science and allocated for ESA core. So thank you very much for your attention and for attending the seminar today, and I'm more than happy to take questions.
Thank you very much, Professor Tinetti. Professor Ip should be back soon. Yeah, indeed, there are some questions, and also people thanking you for the excellent presentation.
Can you see some of the questions?
Yes.
Professor Tinetti?
Yes, I can. Should I start to answer them, or how do you suggest?
You do some of them. You know, you like.
We can first read them out loud so that we make sure that everyone knows what the question is. So first of all, from Professor Rafael Garcia, will Ariel have the capability to observe solar system planets, for example, Jupiter or Venus?
Okay, thank you. Great question. The answer is yes, but certainly not Venus. Venus is really way too bright. Question mark for Jupiter, but we're certainly looking into that right now. I would put my bet more on Neptune, Uranus, but we're also looking at the possibility of doing Jupiter. So more very soon.
Okay, thank you very much. Is it possible to study the transient modification of atmospheric chemistry produced by stellar storms, for example, space weather effects?
Okay, this is another very good question. There was a very interesting paper some years ago led by Olivier Venot. They looked at the effect on chemistry after some stellar flares. And they showed that in principle, you should be able to see some modification in the chemistry. So in principle, if we are targeting planets around very active stars, we might be able to look at some of these effects. Of course, the issue with the extremely active star, in particular the one that are flaring, it means that you need to be careful then in correcting the data from the stellar activity. So we certainly want to include a few examples in the sample of planets around very active star to try to address exactly this question. But of course, we can't really have too many targets around the extremely active star because they are potentially relatively difficult to analyze.
Thank you very much. Then we have a question from Michel Blanc. Can you tell us more about the physical contents of Ariel data products, spectra, atmospheric compositions, atmosphere structure models, others?
Yes, of course. So in the assessment report or red book that we presented to ESA and is available on our website and was already put as a link in some of my slides, you have the full description of these data products. But basically, what will be publicly available when we release the data is a level 2, which is typically better in terms of correction of the systematic or what normally now we are using for Hubble, for instance, for Hubble or Spitzer. And so typically these are light curves, correctly light curves. And then from the light curves to the spectra, then is the step from level 2 and from level 3, but level 3 is already a science project. So the consortium will also put out, of course, the level 3, but that might take a little bit more time because it needs to go through peer review. But level 2, which is, as I said, slightly better or what we are used to from Hubble and Spitzer, will be out with according to this rule. Of course, all the description of the level data is, as I said, very detailed in many ESA documents. And so if you have any question, I'm more than happy to point at those documents so you can read more in detail what we're planning to do.
Thank you very much. We have a thank you also from Carl Bergquist for the very instructive presentation. And then another question from Professor Michel Blanc. What is your view on the long-term perspective in this domain of exoplanet atmospheres and habitability beyond Ariel and JWST? You can read the question.
Yes, of course. Well, I must say that sometimes it's very hard for exosolar planets to to see an horizon that goes beyond the next generation of missions, simply because we're all getting used in exoplanets, that many surprises are happening, and many discoveries then are basically pushing us towards a different direction. So it's not really so obvious to see beyond Ariel and James Webb, not because I don't believe there is an obvious step forward, but what is the technique that we should use to look at habitable planets? It's more going towards direct imaging, or more pushing for transit technique. For habitable worlds, I think James Webb will already deliver, I think, probably very important information for small planets in the habitable zone, or M-dwarf, through the transit technique. But if we want to push at the habitable zone of more G-type star like the Sun, then and if we want to look at the atmospheric composition for those specific planets, then transit starts to become impractical, because you have to wait quite a lot of time before you're completing the transit. So probably direct imaging seems to be the most obvious way to go. Which technique to use, then again, we're all discussing in the community, not always obvious. We're all talking about big facilities and also expensive facilities. But I think the results of James Webb and Ariel will be very important to guide also the next steps. So I'm really looking forward to see these results.
Thank you very much. And then next question is from Bernard Foing. Apologies if I mispronounced the surname. How do you plan to involve further the AI machine learning community in preparation and analysis?
Thanks so much, Bernard. Great question. So we have already a good team in-house in the consortium working on AI and some of these techniques to analyze the data. But because we want really to make sure that we involve the entire community, we will certainly continue this data challenge tradition. And the data challenge for 2021 that I was mentioning, also this time is done in collaboration with the European Conference on Machine Learning, which typically really attracts a lot of participants. What we want to do in the future is making sure that this message and the data challenges will be advertised also well beyond Europe, making sure that is the global community of AI that is participating to these data challenges. So it's certainly in our agenda to make sure that these data challenges are really reaching the global community. And data challenges are one way, not the only way, but certainly one way to get the interest of those communities.
Thank you very much. Next questions. Can Ariel detect life, and what's next after Ariel?
Okay. I don't think Ariel will be able to detect life. Well, first of all, detecting life, I think we all need to be a little bit careful in what we're considering biosignature or not. But apart from jokes, I think Ariel will do great for planets that are warm and hot. And we probably have the chance of pushing towards more temperate planets, in particular for Neptune's or gaseous planets. For small planets to be temperate and being able to observe that area, I think we really need to have an extremely favorable combination of star and planet. So we are not necessarily advertising this as a possibility, because it might be the case or it might be not. But I think James Webb will definitely have the opportunity of looking at planets like the TRAPPIST, for instance, the TRAPPIST-1 system. And so we're all looking forward to see what we will see, whether we will see any signatures that we could consider a biosignature. Although I am personally convinced that we all need to be a little bit careful in pushing for the detection of biosignatures, because there is so much more that we need to know about those planets. We're really just starting this exercise. And so I think there is still a long path to go before we really understand the the habitability question in a meaningful way.
Thank you very much. And then Masaki Nishino, since Ariel will be capable of observing the solar system objects, it will be interesting to examine asteroids and comets as well as interstellar objects. It's more of a comment than a question.
Yes, so there is a working group in our consortium that is exactly looking at all this. So they will probably publish a paper at a certain point. And this information could be useful, in particular for the time dedicated to our science through the ESA call. But so we certainly plan potentially to use some of the solar system objects as calibrators. So they might also come for free in a certain sense.
Thank you very much. And then, since it's the final question from Xiaoming Huang, thanks a lot, Professor Giovanna Tinetti. Will Ariel promote the detection or verify the high altitude winds and atmosphere escaping the transiting Neptune mass exoplanet by using high resolution observations?
Okay, that's an excellent question. Given that Ariel is not necessarily looking at the UV, it's not able directly, perhaps, to put some constraint into the escape properties of these atmospheres, because for that you typically need to have the UV observation. But what Ariel will be able to do is to give you the big picture, which is out of planets with this size, for how many of these planets we're still seeing some hydrogen and helium or not. And to me, this is a way to answer in a population way to these questions about how important is the photoevaporation, because of course, if for planets with a certain size, we're all seeing that these planets have completely lost hydrogen and helium, that puts a pretty strong constraints in the photoevaporation and its efficiency.
Thank you very much. We also have a thank you from Professor Bernard Foing, again, the surname. And I see no other questions. Professor Ip, maybe do you have any questions?
Yeah. No, I think that because my connection here is not so good, so I missed some of the Q&A. But and I just want to thank Professor Tinetti for a wonderful presentation, and I hope that we will invite her back now to give talks. Not wait until the launch of Ariel, because this field is moving so fast, and there are so many other things happening, and she's doing so many interesting things. I hope that Professor Tinetti will promise to do that.
Absolutely. Well, first of all, Professor Heap, thank you. Yeah.
Thank you, everybody, for coming to this, webinar, and then
I can't hear Professor Ip anymore. I don't know if it's my
maybe
connection.
Lola, you could finish the talk now.
Yes, absolutely. If, unless Professor Tinetti has anything else, something else to add.
Yes, I would like to thank really sincerely Professor Heap and you, Laura, and all the team and ISSI-BJ. It was a really great pleasure to do the seminar this morning, and definitely I'm looking forward to another seminar in person, because I absolutely want to come to China again very soon. So yeah, it's a promise. As soon as it's possible, as soon as there is a flight that gets me there, I really hope to be able to do that very soon.
I think we'll the session for now.
Sorry? Thank you very much, Professor Tinetti. I'm not sure if Professor Zip's connection is very good. You're always welcome here at ISSI-BJ. And to wrap up the seminar, we're going to have the next one on the 24th of February with Professor Johannes Benkhoff on the Bepi-Colombo mission, and especially it's going to be on the Mercury magnetospheric orbiter. And so it's going to be more than 2 weeks because we're going to have Chinese New Year in between. Thank you once again. And once again, you're always welcome here at ISSI-BJ, provided that the situation allows it. Thank you very much once again.
Thank you so much. 谢谢。
谢谢。
Bye.
Bye-bye. Bye-bye. Bye-bye.